It beats for you, so listen close. Hear my thoughts in every note. Oh, oh. Make me your radio and turn me up when you feel low. This melody was meant for you. So sing along to my stereo.
Class heroes, baby. If I was just another dusty record on the shelf, would you blow me off and play me like everybody else? If I asked you to scratch my back, could you manage that? Like if we had chicken Travie, I can handle that. Furthermore, I apologize for any skipping tracks. It's just the last girl that played me left a couple cracks. I used to, now I'm over that. Cause holding grudges over love is ancient artifacts. If I could only find a note to make you understand, I sing it softly in your ear and grab you by the hand. Just keep me stuck inside your head like your favorite tune. And know my heart's a stereo, the only place for you.
My heart's a stereo. It beats for you, so listen close. Hear my thoughts in every note. Oh, oh.
Come on.
Make me your radio and turn me up when you feel low. This melody was meant for you, so sing along to my stereo.
Let's go! If I was an old school 50-pound boombox, would you hold me on your shoulder wherever you walk? Would you turn my volume up in front of the cops and crank it higher every time they told you to stop? And all I ask is that you don't get mad at me when you have to purchase Mad D batteries. Appreciate every mixtape your friends make. You never know, we come and go like on the interstate. I think I finally found a note to make you understand. If you can hit it, sing along and take me by the hand. Just keep me stuck inside your head like your favorite tune. You know my heart's a stereo, the only place for you.
My heart's a stereo. It beats for you, so listen close. Hear my thoughts in every note. Oh, oh. Make me your radio and turn me up when you feel low. This melody was meant for you, so sing along to my stereo. Because good music can be so hard to find.
So hard to find.
I'll take your hand and hold it closer to mine.
Yeah.
Our love was there, but now you're changing my mind. My heart's a stereo. It beats for you, so listen close. Hear my thoughts in every note. Oh, oh. Make me your radio and turn me up when you feel low. This melody was meant for you, so sing along to my stereo.
It's your boy Travie. Gym Class Heroes, baby. Yeah.
Hey, where's the drums?
Hi. So today we will just be continuing with last week's chapter. So first, I'm just going to present the same PowerPoint from last week, and we'll just run through the chapter very briefly again. So if there are any questions, you can just use the mic or just type it out in the chat box. All right, so we'll be continuing with the chapter congruency, enlargement, and combined transformations. So, alright. So congruency, it's just about pairs of objects that have the same size and shape, regardless of their position and arrangement. So we'll just very briefly run through these. And one thing that's important to note for this subtopic is the triangle congruency. The side angle side, all of these. And it's important to remember that SSA and AAA cannot be used to determine the congruency of two triangles without the area. So next is enlargement, which is basically a transformation in which all the points of an object move from a fixed point with a constant ratio. So the fixed point is known as the center of enlargement, and the constant ratio is known as the scale factor. So for enlargement, the important points are center of enlargement and scale factor, which is also symbolized by K. And you can see that there are two different ways to determine the scale factor. The first formula is by dividing the distance of point of image from the center of enlargement over the distance of point of object from center of enlargement, or you can use length of side of image over length of side of object. So the common ground you can see here that it's always the image divided by the object. And one of the important formulas you have to remember is I equals to OK square, which is to find the area of image from the area of object and the scale factor. So as for congruency and enlargement, we already, Idris already did exercises for that last class. So for this class, we'll mostly be focusing on combined transformation and tessellations. So we will just run through these two subtopics again. So combined transformation, it's defined as one transformation followed by another transformation. So what are the different types of transformations? So we have translation, which is just basically moving your object. So the image will be in a different position, but it will still be congruent. So it's still the same shape, same size. It will just be in a different position. And then you have reflection. And reflection is just the object is mirrored according to its axis of reflection. And you have rotation, which is just basically turning the point. So it won't necessarily be congruent anymore. Your object won't be congruent anymore. It will still have the same shape. It will still have the same size, but it just won't be in the same orientation. And finally, we have enlargement, which is we already touched on it earlier, but it's basically just the size of the object will change, but the shape of the object remains the same. Right. So how to determine the image and object of a combined transformation. So one important thing to note is when it says something like combined transformation AB, it means you have to do the second letter, the transformation according to the second letter first, followed by the transformation of the first letter. So in the exercises later, we will touch on that. But yeah, this is just one thing to note because it can be confusing sometimes. So on the right, you can see if we use P as the object, using combined transformation AB, if you undergo transformation B, you will get P prime. So that will be your first image. And then because it's combined transformation AB, you still have to undergo transformation A. So P prime, when you put it under transformation A, when you put P prime under transformation A, you'll get P double prime. So that will be your final image. Yeah. Right. So how to determine if a combined transformation satisfies commutative law. So basically, just to refresh, commutative law, an important point is that when you put an object under a combined transformation, let's say combined transformation AB, if the object under combined transformation AB produces the same image as the image produced under transformation BA, then it satisfies commutative law. So this is one of the most important points when it comes to this subtopic. So we'll just go over here briefly at the end. So translation, this is just basically how you want to describe the different types of transformations. So for translation, you'll need to mention the units moved and in what direction, and the direction will be shown through negative or positive. Rotation, your important points will be center of rotation, degree of rotation, and direction, which is clockwise or anti-clockwise. As for reflection, you will need your axis of reflection. And as for enlargement, you need scale factor and center of enlargement. All right. So the final subtopic is tessellation, which is defined as a pattern of recurring shapes that fills a plane without leaving empty spaces or overlapping. So basically, we already went over this exercise. So tessellation is just basically shapes that occur repeatedly. So basically, it's a pattern, and because all of these are tessellations except for B, the reason why B over here is not a tessellation is because although the equilateral triangles and the isosceles triangle are repeated, the square in the middle only appears once. So because it doesn't repeat, it's not considered a tessellation. And so isometric transformation is the transformation that produces an image that is congruent to an object. So basically for this part, you'll be given a shape, and from there you will sort of form a pattern using the concept of transformations from that one shape to form a pattern according to that one shape. So that's it. So now, right. So now, I'll just be going through some example questions so that we can sort of understand this the combined transformation subtopic so that we can have a better understanding of it. Right. Right. So as you can see here, we'll do example 10. So just remember, if you have any questions, just type it in the chat box or just use the mic. So given that T is a translation, right. So as you can see here, given that T is a translation, so for me personally, when I see, because sometimes in maths the questions can be a bit wordy. So just to make it like easier for myself, I like to underline the main points. So for this subtopic especially, uh, I recommend that you sort of highlight or underline uh, like specific letters with transformations. So like this one, T is a translation. So make sure that you sort of highlight that. And then NP is a reflection in the line y equals to 2. So I would underline this as well. So okay. T is a translation. So as for this one, the one the number on top, it refers to the movement in the x, and the number on the bottom refers to the movement on the y-axis. All right. So now that we know T is the translation and P is a reflection, trapeziums 1, 2, and 3 are the images of the shaded object for two isometric transformations. All right. So basically what it's saying is that these shaded objects, this is your starting point basically. And then your trapeziums here, 1, 2, and 3, these are so based on the diagram, determine the image of the shaded object under the following combined transformations. All right. So the first one we have here, just refer to this diagram because this is a part of the question. And so these are just the answers, so we can just go through them together. All right. So the first question, A, they ask you in this sort of format, which is like, it looks like T to the power of 2, but basically what this means is that it's actually a combined transformation T. So it's actually you just have to put the object under the same transformation twice, right? So because T is a translation of -1, 2, right here. All right. So here in this answer box for A, I've already sort of outlined the object, which is the shaded trapezium. So now that we know our combined transformation is, we have to let it undergo transformation T twice. If we refer back to the question, T is a translation, -1, 2. So we know that All right. So we know that we have to undergo the transformation starting from the back. So because both of these, the letters are T, so both of them are transformation T. It doesn't really matter, but just remember that the formula is that uh, regardless, you still have to do the transformation from the back to the front. So, all right, because it's negative 1, 2. So because it's negative, it means that we're going to the left on the x-axis. So it would be like this. And then the 2, which means a transformation upwards on the y-axis, means we're going up like this. So that's how you get this right once. So once we've done that, can transformation P. So again, concept, negative 1 means we're going left on the x-axis, so like this. And then 2 means we're going upwards on the y-axis, so 1, 2. And that's how you get this image right here. All right. So just remember that if there's anything that you're confused about, just feel free to use the mic or use the chat box. All right, so next question. All right. So B, we have combined transformation PT. So again, all right. So because earlier we had combined transformation PT, so it didn't really matter which one we did first. But now that we have two different letters, which translates to two different transformations, it's really important that you do the second one first. So in this case, you would do transformation T first, then only you would do transformation P. All right. So looking down at the answer box for B, I'll outline the object. All right. So first, we have to do transformation T. So again, transformation T is a translation of negative 1, 2. So that means we go left 1 unit on the x-axis, and we go upwards on the y-axis. So that's how we get this first image right here. All right. Then we've already done that, we can move on to applying transformation P on the image that we produced earlier. So P is a reflection in the line y equals to 2. So because it says y equals to 2, we can just find on the y-axis right here, 2. And so from there, you can just sort of draw this line. And so the reflection will basically occur here. So usually with reflection, what I like to do is draw it, draw a reference from what you want to reflect. So for example, okay. So because y equals to over here, so I would draw down 2 units. I would just draw down however many units it needs. So in this case, I need to draw down 2 units. And so because I know that this axis of reflection is 2 units away from my point of reference, I know that I should go in the opposite direction with the same amount of units. So from this axis of reflection, y equals to 2, if I have to move upwards 2 units to get this image, then when I want to get the reflected image, the final image, I would move downwards 2 units. And then I would just follow according to the reflection. So that's how I like to sort of do it. All right, so moving on to C, we have combined transformation TP. So again, we want to focus on doing the second transformation first. So we'll do transformation P first, then we'll do transformation T. Right. So, okay, we go through one by one. Again, I'll just outline the object. So if we look at answer box for C, okay, if we do transformation P, again, we refer back to the question. P is a reflection in the line y equals to 2. So the answer box already drew out the axis of reflection. I'll just highlight it again. So because you see that the object is right on the axis of reflection, it's easier. So you just mirror that. All right. So once you're done with that, you can just once you're done with transformation P, you can move on to do transformation T, which is a translation -1, 2. So from the image that we produced earlier, we move 1 unit to the left on the x-axis, and we move 2 units upwards on the y-axis. So essentially, that's how you go about doing questions for combined transformations. So yeah, so now we'll just move on to the next few questions. All right, so for this question number 1, I want to focus specifically on B, but we'll just go through the question, the entire question. All right. So in the diagram on the right, trapeziums 1, 2, 3, and 4 are images of the shaded trapezium under the combined transformations. So all of the numbered trapeziums, they're all images, and your object is the shaded trapezium over here, the one that I've outlined. So given that R is a reflection in the line y equals to x, T is a translation -2, 2, and V is a rotation of 90 degrees clockwise about the point 1, 3. All right. So here you can see that we have 3 different types of transformations. So you just have to do according to the question, whatever the question asks. You don't have to apply all of the transformations. So just stick to what the question wants. All right. So as I said earlier, I want to focus on B specifically. So, all right. So V is a rotation of 90 degrees clockwise about the point 1, 3. So I want to focus on this one specifically because we haven't done a rotation type question. And the other transformation is T, which is a translation -2, 2. All right. So again, looking at this combined transformation, we have to look at the one that comes in second. So in this case, it's T. So we'll have to do a transformation T first before we can do a transformation V. All right. So T is a translation of -2, 2. So that means we move 2 units to the left on the x-axis and 2 units upwards on the y-axis. So basically, we do it like this. Right. So usually for translation questions, I'm sure Idris mentioned it in the last class as well. Yeah, usually you just do it according to one reference point, and then you just sort of flesh out your object from there. So like, for example, I choose this as my reference point. So I'll just sort of copy down the shape according to that reference point specifically. You don't have to really apply the transformation to every single point. So like once you get this, you've already done transformation T. So next you have to do transformation V. So V is the rotation of 90 degrees clockwise about the point 1, 3. So first, you should find the center of rotation. So in this case, it's 1, 3. So it's point 1 on the x-axis, which should be around here, around this line right here. And then point 3 on the y-axis, which should be here. So this is your center of rotation. All right. So once you have this, you need to keep in mind that the rotation that they're asking you for specifically is 90 degrees clockwise. So basically clockwise and anti-clockwise. You just follow. It's very it's self-explanatory in the sense that like ikut arah jam. So clockwise, you sort of turn to the right, and then anti-clockwise, you turn to the left. And then 90 degrees, it's usually, just the general, if we move like this, it's 90 degrees. If we move like this, then it's 180 degrees if we move from that starting point. And one thing to keep in mind is that usually in rotation questions, if they ask you to rotate your object 180 degrees, they won't give you clockwise or anti-clockwise, because either way, if you rotate it anti-clockwise or if you rotate it clockwise, 180 degrees, you'll still get the same shape. So it's sort of redundant law. All right. So now that we have our center of rotation, again, you can just take 1 point. So just to make things easier, I'll take this point right here that's directly below the center of rotation. And then because they're asking for a rotation of 90 degrees clockwise about the point. So because clockwise, basically you have to rotate it to the right. Right. So from there, you would rotate it this way. Right. So once you rotate it this way, you can sort of draw back the amount of units that you drew to your point of reference. So in this case, it's 1, 2, 3. So because we've already established that you're rotating it in this direction, we can count it back to 1, 2, 3 units. And then you can see that this will be the image produced. Again, just draw according to the point of reference. And from there, you can sort of just draw it out according to 1 point only. You don't really have to apply it to all of the points. All right, so if there's anything you don't understand, just be sure to speak up or just say something in the chat box, because I'll just be mostly moving on and I won't be doing every single question. So I will just be doing certain select questions that I feel need a little bit more focus on, because honestly, this subtopic, it's quite repetitive. So I think it's better to just save time doing a few select questions. All right, so for exercise 11, for this one, I will go through the entire thing. All right, so in the diagram on the right, quadrilaterals 1, 3 image updated under the combined transformations. So again, the quadrilaterals that are numbered are the images, and this shaded quadrilateral over here is your object. All right. So given that P is an enlargement of scale factor 2 about the origin, so origin, it's basically 0, 0 on the Cartesian plane. It's where the x-axis meets the y-axis. So just remember to highlight that as you go along. Q is the translation -3, -4, and R is a reflection in the y-axis, right? So when they ask for a reflection in the y-axis, it's basically just a reflection along. It should be easier as it's already drawn out the y-axis, but yeah, it's just along that one line over there. So here they're asking you to determine the image of the shaded object under each of the following combined transformations. All right. So here for A, we have P, again, it looks like P to the power of 2, but in reality, they're asking us to undergo combined transformation P. So again, because it's the same letter, so essentially it's the same transformation. You don't really have to worry about which transformation you're going to do first. So we just have to do transformation P 2 times. Right, so again here, P is an enlargement of scale factor 2 about the origin. Okay, so basically what they're asking for. Okay, so this is the center of enlargement because of the origin, so it's 0, 0. So when they're asking for scale factor 2, basically what they're asking for is you to sort of draw it out and equate it to the ratio, which is the scale factor. So here you can see, let's just say this is my point of reference. Again, one of the formulas we had earlier is the distance of the image from the center of enlargement over the distance of the object from the center of enlargement. So for this one, we'll just be using that formula. All right. So this is my point of reference. So this is 1 unit away from the center of enlargement. So if the scale factor is 2, and that means that if my object is 1 unit away, then my image should be 2 units away. So my point of reference for this point specifically, so if I were to draw it out, it would look like this. All right. So for this specific point, it would look, so we already know that one point is over here. And then let's say if we use this reference point, because this is 1 unit away, again, we have the same case. So the image should be about 2 units away. So then it would look something like, it would look a bit like this. So basically what happens here is that it just doubles in size because of the scale factor 2. So once you have this, we already did transformation 1. So you have to do it. So now same concept. Right, it's the same concept because this is your first image. So again, we're using the same formula. This is away. So because now it's 2 units away, and then the distance of the image from the object, the distance of the image from the point of enlargement would be 4. So again, 1, 3. So see, because we already sort of have the options laid out for us, if you carry on, doing it this way as well. So because we're using this as a reference point now, and you can see that from the point of enlargement, it's 2 units. So because the scale, we know that the distance of the image from the object is 4 units. From there, you can sort of already know that this is the shape. And it will just mostly double in size. So again, like earlier here, you can see that the base was 2 units, or over here, but it's not so clear, but over here it was only 1 unit, and then it became 2 units over here, and that is 4 units, because it's basically just times 2 and times 2 again. All right, so that's just how you do enlargement as part of the combined transformation. Next we'll move on to B. So for this one, it's combined transformation PR. So again, just take note that you have to do the second letter, the transformation under the second letter first. So in this case, you're supposed to do transformation R first, and then move on to transformation P. All right. So here, R is a reflection in the y-axis, and P is an enlargement of scale factor 2 about the origin. So again, make sure you sort of have your object you've determined which one is your object. So once you've done that, just because R is a reflection in the y-axis, um, so just determine your axis of reflection, which should be right here. And because again, this question, it's a bit easier just because you know your object is directly on the axis of reflection, so you can just sort of mirror it. Right. So your reflected image would look something like this. Okay, so now you've already done transformation R. So to do transformation P, again, it's an enlargement of scale factor 2 about the origin. So this is the origin. So if I use this as my point of reference, again, because the distance of the object is 1 unit away from the point of the center of enlargement. So the image would be, because the scale factor is 2, just take 1 times 2, so you will get 2 units. So the distance of the image from the center of enlargement is 2 units. So again, you'll get this point. And then basically, same concept, everything is doubled because of the scale factor. If the scale factor was 3, then it would be tripled. So basically, it's just a matter of multiplying it with the scale factor. So like here, you can see that this base, it was only 1 unit, and here it's 2 units because the scale factor is 2. So basically, that's just how you go about with B. All right, so moving on to C, Q combine transformation QP. So again, just determine which transformation you need to do first, which in this case is P, followed by Q. So P is an enlargement of scale factor 2 about the origin, and Q is a translation of -3, -4. So if we're doing P first, then that means we have to put this object under enlargement first. So earlier, for question A, we sort of already figured out the enlargement if we were to do it directly from this one. So again, it's just distance of object from the point, the center of enlargement, it's 1 unit. So then if we were looking for the distance of the image from the center of enlargement, be 2. And then here, again, if it's 1 unit over here, then it would be 2 units. Then it would look like this. Okay. All right. So you would think that looks like this. So once you've done that, then you have to put this image different form. Again, the -3 denotes that you move towards the left on the x-axis 3 units. So 1, 2, 3, assuming this is your point of reference. And then -4 means that you have to move downwards according to the y-axis. So 1, 2, 3, 4. So again, because it's a translation, the shape is mostly congruent. So it's just basically the same shape, but in a different position on the Cartesian plane. So that will be all for this specific question. So then we'll just be moving on. All right. So for this one, we'll mainly focus on question 1. All right. So in the diagram above, triangles 1, 2, and 3 are images of the shaded object for the combined transformations. So again, this shaded triangle right here is your object, so it's your main point of reference. Okay. So given that R is a rotation of 90 degrees anti-clockwise about the origin, T is a translation of -1, 4, and E is an enlargement of scale factor 2 about 0, 1. Right. Again, R is a rotation of 90 degrees anti-clockwise about the origin. So that would be 0, 0, your coordinates. T is a translation of -1, 4. And E is an enlargement of scale factor 2 about 0, 1. And P is a reflection in the line y equals to 1. So for this one, it's quite simple. We just have to label the quadrilaterals according to what the question wants. So going through one by one, if we're looking A, basically what they're asking for is a combined transformation TE. So again, just sort of list down in what order you need to do the combined transformation. So in this case, it's transformation E first, then transformation T. All right. So this is your object right here. Then transformation is an enlargement of scale factor 2 about 0, 1. So that means 0 on your x-axis and 1 on your y-axis. So this would be your center of enlargement. So if scale factor 2, then we just apply the same formula as just now. So if the object is 1 unit away from the center of enlargement, then the image should be 2 units away from the center of enlargement. And from there, we can sort of just multiply it by 2. So essentially, this would be your the first image produced by transformation E. And if you want to double check, then you can just draw a line according to your point of references. So it's basically the same point, because essentially with enlargement, you're drawing the same shape, just different sizes. So you can link up the points that are equal to each other. So this one will be the same as this point. And if they all add up to your center of enlargement, then essentially you're on the right track. Right. So once you've done the first transformation, which is E, next you have to do transformation T, which is a translation of -1, 4. All right. So -1, 4. It's basically just 1 unit to the left on the x-axis and 4 units upwards on the y-axis. So let's say this is my point of reference. Right here, this is my point of reference. So I'll move 1 unit towards the left. Give me a moment, yeah? All right. So basically, okay, so basically, T is a translation of -1, 4. So you just move it uh so you just move it 1 unit to the left and 4 units upwards. But I think I might have made a mistake. So just give me a moment. Yeah, I'm so sorry. All right. So essentially, what happened was I made a mistake in the enlargement. So I'm just going to go backtrack to that. So E is an enlargement of scale factor 2 about 0, 1. So this would be your point right here. Oh, I made a mistake in the center of enlargement. So basically, it would be 0 along the x-axis. So essentially, it would be somewhere along this line, and then 1 on the y-axis. So this would be your point of enlargement right here. All right. So again, if this is 1 unit, then your image would be 2 units. So it would be here. And then from there, I'll just quickly draw out the enlargement. Right. So if we undergo the transformation, the translation and negative 1/4, we move it 1 unit to the left and then 4 units upwards. Then you can see that we already have the image up here. So for A, your answer will be 2. Right. So moving on to B, a combined transformation EP, again, just determine which transformation you need to do first. So in this case, it's E first, followed by P. All right. So E, again, E is an enlargement of scale factor 2 about 0, negative 0, 1. And P is a reflection in the line y equals to 1. So because we sort of already have the drawing of the reflection, the enlargement here, we can just jump ahead to doing P. All right, so this is the image produced by the enlargement. So P is a reflection in the line y equals to 1. So here, this is your line y equals to 1. All right, so with reflection, again, what I like to do is, just determine a point of reference. So in this case, I'll be using this one. And then from this axis of reflection, I like to count in what direction and how many units I need to move to get to that point of reference. So in this case, I need to move upwards by 2 units. So because it's a reflection, to produce the image of reflection, I'll go back to this axis of reflection and I'll move in the opposite direction in the same amount of units. So that would be downwards 2 units. So again, I'll get this reflected point of reference. And from there, you can already determine that quadrilateral tree is the answer for B. All right, so moving on to C. All right, combined transformation ER. So again, just determine which transformation you need to do first. In this case, it's R followed by E. All right, so R is a rotation of 90 degrees anti-clockwise about the origin. All right, so for R, first we'll just determine the point of rotation, which is origin, so it'll be here. And then again, just determine what point of reference you want to use. So I'll just be using this one right here. And then I'll just draw a line connecting that point of reference to the origin. And then because they're asking for me to rotate it 90 degrees anti-clockwise, so basically we're rotating it in this direction. So it would move something like this. And then what I like to do is I like to count it this way. So it's 1 unit here and then followed by 2 units. And then you just sort of rotate it. So let's say if you move 1 unit on the x-axis and 2 units on the y-axis, now you move, you just sort of turn it around. So now you move 1 unit on the x-axis and 2 units on the y-axis, and then you just join it like that. So that's what I like to do essentially for rotation questions. And then from there, you can just draw out according to your point of reference. So again, because this is my point of reference, I'll just draw it out according to that. All right. So now that we have already gone through transformation R, we can move on to transformation E, which is your enlargement of scale factor 2 under center of enlargement 0, 1. So that'll be here. All right. So again, if your object is 2 units away from the center of enlargement, then because the scale factor is 2, it's basically 2 times 2. So your image will be 4 units away from the center of enlargement. So we can see that quadrilateral 1 follows the is the one that fits in the requirement for this sort of transformation. So from there we know that for C your answer is for C your answer should be quadrilateral 1. So again, if there are any questions, you can just ask in the chat box or use your mic. But if not, then maybe we can take a 3-minute break right now, and then we'll come back at 9:25. All right. So we'll just continue from here. So basically, a lot of the questions, because with combined transformations, it's just very repetitive. So basically, once you already know how to draw, and I think because we've already gone through every single type of transformation, I think what's left for this subtopic is basically transformations. All right. All right. So earlier in the PowerPoint, I already pointed out which sort of points you need to address when describing transformations. And the way I was taught when it came to describing transformations, basically you don't really have to write it out, but then again, just answer however your teachers in school tell you to do it. But basically, what I was taught was that you don't really have to write it out in a sentence. You can just write it out in points, as long as everything important is there. So just for the sake of this class, I'll just write it down in points, just so that it's sort of brief, it's not wordy, and it's easier to just see where the main points should be. All right. So in each diagram below, quadrilateral PQRS, all of them are prime, is the image of quadrilateral PQRS for transformation X, followed by transformation Y. All right. So for this one, basically, first, you have to determine which one is the object and the image. So again, you can see here they already labeled PQRS prime, that's your image, and PQRS, the one without prime, that's your object. So I'll just highlight the object. All right. So here, they said transformation X followed by transformation Y. So that means this object, it underwent transformation X first before going through transformation Y, which means your combined transformation, when you write it down, it should be written as YX, because you did transformation X first, then you did transformation Y. And as we know, if you sort of have the combined transformation presented to you in this sort of format, you have to do the second transformation first. So which is why it's written down like that. All right. So for A, all right, you can see that the shape is still the same, but it's inverted. So basically, from that, you can deduce that one of the transformations is a reflection. And then, as you can see also, the image and the object, they're not the same sizes. So from there, you know that one of the transformations is an enlargement. So for me personally, I don't really know how to sort of describe it, but then I think for me, I can sort of see that a reflection happens before the enlargement. So basically, what I like to keep in mind is that usually when you have a transformation, usually my first instinct would be to assume that the enlargement is the second transformation. And obviously, this doesn't apply to every case. But then it's just something to keep in mind, that the possibility of the enlargement being the second transformation is higher than the possibility of the enlargement being the first transformation. So right now, I'm just going to write down that the first transformation is a reflection. So, uh, okay. So right here, when it comes to enlargement, I sort of like to narrow it down to the middle. So basically, but honestly, when it comes to enlargement, you can just do it at any point, as long as you know how to sort of as long as you know how to find the right center of enlargement. Which is why, honestly, questions like these, sometimes you can have multiple answers, especially when it comes to enlargement, because you can do it from different points and you can still get the same answer. So for this one, just for the sake of the example, um, I'm going to say that a reflection occurs in the line x equals to 1. So then basically what you're going to write down is reflection. What you're going to write down is reflection in the line x equals to 1. So that would be your first point. So that would be your transformation X. So next, as for transformation Y, first I'll just sort of draw it out like what the reflection looks like. So again, this is 1 point away from the axis of reflection. So I'll just apply the same one here. And then you just sort of draw it out. Okay, so now that you have your first image, and then from there you can sort of deduce that you have the same shape and it's a different size because we already established earlier that one of the transformations is enlargement. So from there, to find the center of enlargement, you can just join up the points and then see where it all sort of meets up. So just let me make it like a little bit neater. All right. So basically, the answer for this specific example, um, it's honestly quite complicated because the center of enlargement, it's on the point 3.5 to 1. So honestly, I wouldn't really go with something like a point to see if there's any way to just find another center of enlargement without making it as complicated. Because again, sometimes questions like these, you can have multiple sort of answers. Right. So I think this is an answer that I would have given myself. So basically, what I would have done, not following the answer, I would have just done a reflection in the line x equals to 0. So basically, I would have done a reflection in the y-axis. So basically, it would have produced this image. And then from there, you can just draw lines that connect according to the points given. So as you can see, they all sort of meet up at this point right here. So this specific point, it's still a sort of a halfway coordinate. So it would be 0.1 on the y-axis and 1/2 on the x-axis. All right. So 1/2 on the x-axis and 0.1 on the y-axis. And from there, you can just from this point, you can just determine if this is 1 unit away, this point of reference, then we'll just take this one, the one that corresponds to that point of reference. Then we can see it's 3 units away. So the scale factor would be 3. So then your important points to write down would be reflection, I'm sorry, enlargement, with of scale factor 3 at center, and then you just insert the coordinates, which in this case would be 1/2. 1/2, 1. Right. So again, because we've already sort of covered reflection and enlargement, and I don't really want to take up the time that's allocated for tessellations. So I'll just sort of brief on the important points regarding translation and rotation. So, all right. So for rotation and translation, all right. So for rotation and translation, translation should be one of the easiest. So usually you just have to apply, you just have to, all right. So we can just use this for a translation example. So assuming that these are just the same points, so then you can sort of see that the distance between these two, just disregard the fact that it's different sizes. We'll just assume that this looks like this. We'll just assume that it's still the same size, just for the sake of describing the transformation. All right. So you can see that on the x-axis, it's 1, 2, 3, 4, 5, 6 units away on the x-axis. It's 6 units towards the right. So when you write it down, it should be 6. So your value should be positive, not negative. And it's 1, 2, 3, 4, 5 units upwards. So when you write down this, when you describe a translation, you should say that X is a translation of this one, and then you just write that down. So that's how you describe a translation. And for rotation, the way you describe that, basically what you do is you just your important points should be center of rotation, the degree of rotation, so it's 90 degrees or 180 degrees, and the direction, which is clockwise or anti-clockwise. And again, just remember that if your angle of rotation is 180 degrees, you don't really have to write down the direction, whether it's clockwise or anti-clockwise, because it's quite redundant. So just keep in mind those 3 points: your direction, your angle, and uh, your direction, your angle, and your center of rotation. So I believe I think we can just take a 5-minute break or 6-minute break and just come back at 9:45, and then from then on we'll continue with tessellations.
All right. Hello. Uh, I'll be taking over the last 15 minutes. Thank you, Pravina, for teaching the earlier class. So carrying off from when Prav stopped just now, we are going to be doing tessellations. So in SPM, tessellations aren't really, well, from what I've seen from much of the analysis of previous questions, tessellations won't really be asked. So this is more of a general knowledge kind of thing, which you can just look at and be like, oh, that's cool. And then see some applications in your life, you know? So let's just look at this topic first. So 5.4, tessellations. Follow the following steps and form a tessellation. Okay, so this definitely, I don't think will be asked in SPM because there's no way they're going to ask you like to draw shapes like this. But let's just look at the workbook for a bit to understand what exactly tessellations are. Tessellations involve basically just repeating patterns. So I don't know why they give you all these steps to form the shape, but let's just look at it for a bit. So we have step one, they're just giving us a regular square over here. Okay, simple enough. And then they're splitting that square into two. And then for some reason, that becomes this. And I don't really see how that correlates, but we'll go with it. So it's formed into four shapes now instead of two. And now from step three, we go to step four. They've separated all the four shapes. And now what we can see is they've actually inverted it. Okay, they've inverted it. So basically like they flipped it over. Imagine these as four sheets of four different sheets of paper, and you're flipping each piece around. And that is the final shape that we have here. So looking at this final shape, basically a tessellation would involve repeating this shape multiple times. And a real tessellation will go on indefinitely, meaning it'll extend to infinity and beyond, and not just involve these 6 squares, you know? So basically a tessellation will go on forever. So you would just keep drawing. Yeah, a reason why this wouldn't come out in an exam is because there's a lot of drawing you have to do. But basically, you just keep drawing this until it went on forever, basically. So it just goes here, here, here. This wouldn't be called a true tessellation because it's finite. So yeah, that's basically how tessellations work. They're just repeating patterns again and again and again. Okay, so let's look at the second example. Okay, yeah, this is another example which involves drawing, but let's just do it for fun. Okay, so we have step one, just regular square. Then step two, they cut a semicircle into the square. And now step three, they cut a triangle into the square. Now they're taking the semicircle out, they're taking the triangle out, and then they're putting it on top here. That's the final step. And then they're putting the semicircle over here. So how would you form a tessellation from this? So this is going to involve some drawings. So just bear with me. I'm on a tablet, so I can't really draw well right now, but we're going to try regardless. So basically, the pattern would just keep on going indefinitely. What makes a tessellation is that it can just go on forever and forever. It doesn't have a limiting factor to it. These shapes are able to be tessellations because you can just connect them for an infinite number of times. And you can do it either way. You can do it from right to left or left to right, or you can do it from up to down. And that'll work as well. As you can see, we can connect these from all different sorts of angles. And it's pretty cool that we can do that because shapes such as these allow us to make things like, okay, for example, you want to optimize some space for stacking stuff. So in order to optimize, for example, you want to stack crates on top of each other. These squares would be considered a tessellation because it takes up most of the space. Okay, or for example, if you have like a wonky type of packaging that you need to stack up indefinitely, for example, this could be like a chair or a table or something. So allowing that to have that a tessellation shape allows you to stack up these chairs as high as you want without wasting any space. So that's the cool thing about tessellations. They help you optimize space without having to waste any. So it's very efficient for packing, manufacturing, and industrial stuff. And it's a reason why you're learning it, even though you're not getting tested about it that much in the exam. Because the beauty of learning it is that you can just apply it to everyday things. So there's this one more drawing one. I'm just gonna copy and paste the answer from the answer scheme because I don't think I'm gonna have enough time to show you the other question that might actually come out. So let me just copy and paste the answer from the workbook. Hold on. Okay. Oh God, hold on. Okay, so I don't think I can paste that on the page, but okay, it should appear now. Okay, it should be syncing. Okay, let me just draw out a simple sketch so that you guys will know what it'll look like. So it'll basically be like this. And then it'll just go on repeating forever. And this can optimize space, for example. If you're, what is an example of space saving? You want to stack some cans up, you want to stack like boxes, you want to stack like milk cartons, you want to stack up some supplies. Rockets are actually made using tessellations because they allow you to optimize space saving. They allow you to optimize the space you already have as a limited resource so that you can get as much matter as you can into the orbit because it takes a lot of money and energy to get stuff into orbit. So tessellations are a very useful tool that astronomers use to get as much as they can up to space without, burdening their wallets too much. Okay, so it's finally synced in. So this is what the tessellation would look like for, where is it? For over here, yeah, that is what the tessellation will look like. This is a prettier version of the tessellation shown over here. So now, let's look at question 16, an actual question that might come up for exam. So, design a tessellation involving two combined isometric transformations A and B. So in A, we have translation D to C twice. As we learned just now, let's just call this transformation X. Pravina just now taught you about transformations. So since it's twice, it would basically be X squared, or it's just XX. Okay, so you're applying it twice. So you have a translation from D to C. So basically, you're moving this to this, and then this to this. Okay, and the original shape doesn't disappear. It just stays along with the other shape over there. Now you have a reflection in the line DC. So this is the line DC. As Pravina did just now, you would reflect it over this line. So when you reflect it, you would actually get this. But since we need a tessellation, it's not, the rules for tessellations don't completely apply to normal, what do you call it? Coordinate geometry transformation. I think that's what you call it, yeah. The rules of tessellation don't really apply to that because if you did it like this, you wouldn't be able to fill up this space. So it wouldn't actually be a tessellation. So in order for it to be called a tessellation, you would need to reflect it like this, because then you can just keep adding and adding and adding, okay? So the most important rule for tessellation is that it can be added indefinitely. So make sure to take that into account while answering questions in the exam. Okay, now let's do this question. Question 1. So we have a triangle ABC, and the first transformation is a rotation 60 degrees clockwise twice about point C. So as Pravina taught us just now, that we should highlight the points that are important. So let's just call this transformation Z. So it's twice, so it's z squared. So now, rotation 60 degrees clockwise. Since I can assume this is an equilateral triangle, these are all 60 degrees, okay? Because as you know, equilateral triangles have 60-degree angles. So now, if I want to rotate twice about point C, I would take this triangle and then I would rotate it. For example, I would rotate it over here. Then it would be like this. So this is C. So this is C, and you're rotating it about 60 degrees. Since you're rotating about 60 degrees, this triangle is completely separate from the triangle ABC. And now you have a new point. You have a new point C, which is here. This is your new point C, because what you're doing is, it's basically like, how do I say it? It's like a translation, kind of. You're rotating it twice about the point C. So yeah, this becomes a new point C. And then you will rotate another 60 degrees over here. This is another 60 degrees, and it's completely separate from this triangle because it's a whole 60 degrees to the other side. So that is the first step of the transformation. Now you'll have a reflection in the line BC. So this is the line BC. So let's just draw that shape out again that we drew just now. So a reflection in the line BC. So with this tessellation, we can actually follow the rules of the coordinate geometry that we saw just now, and we can just reflect it normally along the line BC. I think a good thing to take into account is that you're not only reflecting along this line, but you're reflecting along this line. Okay? Any previous tessellations that you made will fall into basically the line that you need to reflect onto. So just doing that, and we'll get a nice shape over here, a nice 1, 2, 3, 4, 5, 6, a nice hexagon that you'll get by following the rules of tessellation transformations. So we have another shape here. We have another hexagon that kind of looks like this one. So the first transformation is a translation in the line BC and reflection in the line CD. So these are actually two transformations combined into one, also known as combined transformation. So the first thing I'll do is reflect it in the line BC. Okay, so I'll reflect it over there. So let's just redraw this real quick. A, B, C, D, E, and F. So reflecting along here, I would get this. I would get this shape right here. So that is the reflection on the line BC. And now you'll have another reflection in the line CD. So it's this line right over here. And that's the pattern you'll get after doing both transformations. So as you can see, hexagon is a shape that we can actually tessellate and we can stack it upon each other indefinitely. And that makes it a great space saver. And it's actually why bees, you know how beehives have this shape to it? There's a reason why they do hexagons and not, for example, circles or triangles. It's because hexagons can tessellate onto each other, so it saves a lot of space while also maximizing the amount of stuff we can put into here. So the last transformation will be repeated reflections. Okay, so that's basically it telling you that it wants to repeat forever. So all you have to do is just tessellate each and every hexagon. Yeah, and basically you just keep doing this until you get to a suitable amount. I'd say about 4 times. So this is a repeated reflection. And if you can see, it kind of looks like a beehive, which is pretty cool, don't you think? So yeah, that's basically the entire topic of tessellations. And with that, I think we have concluded chapter 5 from 5. So as we can look at the time right now, it's around 10. So thank you guys for joining the class. I will hope you learned something today. And yeah, that's it. Thank you for joining. Goodbye, class.